Let's tackle a few review problems from 3.7, which deals with optimization problems. Find the dimensions of a rectangle with perimeter 100 meters that has the largest possible area. So first, I'll draw a diagram. I'm worried about having perimeter 100 meters. That's 2x plus 2y equals 100. And what would I like to optimize? I'd like to optimize the area, which is equal to x, y. I'll use this equation to solve in terms of, let's say, y. So first I'll divide everything by 2. Then I'll subtract x. So y always equals 50 minus x. That means a equals x times 50 minus x. To optimize, I'm going to find the critical values of this function. That means I'm going to take the derivative, probably easiest to distribute, then take the derivative. Where is that going to be equal to 0? Well, it's going to be equal to 0 when 50 equals 2x, or x equals 25. Where is it going to be undefined? Never. So we have one critical value. I'll go ahead and use the first derivative test to say a prime is equal to 0 at 25. Bigger than 25, notice that the area is decreasing. Less than 25, the area is increasing. That means that there is a relative maximum at 25. That kind of makes sense. That means we're actually at a square. This is 25. This is 50 minus 25, so that's 25 as well. So what are the dimensions? 25 feet by 25 feet. Moving on to the next problem. The owner of the Rancho Grande has 300 yards of fencing with which to enclose a rectangular piece of grassland situated along the straight portion of a river. If fencing is not required along the river, what are the dimensions of the largest area he can enclose? What is the area? So, here's the straight portion of a river. Here's my x and my y. Doesn't really matter which one's which. And now 2x plus y equals 3,000. What would I like to optimize? I might like to optimize the area equals x, y. Well, we'll solve it the same way we did the last one. Y equals 3,000 minus 2x. So the area really equals x times 3,000 minus 2x, or if I wanted to simplify that, 3,000x minus 2x squared. I'd like to find the critical values. That's a prime equal to 3,000 minus 4x. It's never going to be undefined. The rate of change is 0 when 3,000 equals 4x, or x equals, let's see, 3,000 divided by 4. So divided by 2 would be 1,500, and divided by 2 again would be 750. So x is going to be 750. If I use up 750 here, 750 here, that means this is going to be 1,500. You could always use this equation to figure it out as well. So the dimensions are 1,500 feet by 750 feet. Maybe you would say long or parallel with the river if you wanted to be really explicit here. And the area would be 1,500 feet times 750 feet. So that would be that many square feet. Okay, looking at the next problem. If an open box is made from a metal sheet 10 inches square by cutting out identical squares from each corner and bending up the resulting flaps, determine the dimensions of the box with the largest volume that can be made. So, I have a 10 inch by 10 inch square box. I'm going to cut out pieces. Let's say I cut out a piece that is x by x. Then I fold along those lines to make my box. Let's see, so I need to determine the dimensions of the box with the largest volume. And the volume of this box, well, notice the base is, however long this is 10 inches minus x minus another x. So one dimension is 10 minus 2x. Similarly, this dimension is 10 minus 2x, and the height of the box is of course x. Well, you could take the derivative here using the product rule, but let's go ahead and multiply everything out. So that's 100 minus 40x plus 4x squared times x, or 100x minus 40x squared plus 4x cubed. So the derivative would be 100 minus 80x plus 12x squared. Well, this is never going to be undefined, so we're just looking for places where this thing would be 0. Wouldn't it be nice if I could reduce this a little bit? I'm wondering where this will be equal to 0. So let me divide everything in sight by, I could at least do 4. If I divided by 4, that would be 25 minus 20x plus 3x squared equals 0. If I wanted a surefire solution, I could go straight to the quadratic formula. We might still be able to factor this, so let's see if we can't factor this. 3x times x might be a good factorization. I need two things that multiply to 25, but they need to add to a negative number. That's a good indication they're both going to be negative. Let's see, we could use 5 and 5. That would get me negative 15x, negative 5 more x. Hey, that looks good. Excelente. So, what are those values that would work best? Let's see. This value here is x equals 5/3 inches. This is x equals 5 inches. Now, this problem, I basically recognized that it was going to act the exact same way as this. I knew that what was going to happen was my one critical value was a maximum. But seeming as I have two critical values, maybe I should go back and explicitly use the first derivative test. The volume has a rate of change of 0 at 5 and at 5/3. Now notice from my picture that the smallest x could be is 0. The largest x could be is 5, because if this cut is in 5, that cut is in 5. I now have a width of 0 and a length of 0. So this volume, I actually know that's my boundary, and that's going to have the volume 0. So that's definitely not my maximum. But I could also just check, okay, looking at this factorization. If I pick a value less than 5/3, so maybe 1, this will be a negative times a negative. That means my volume will be increasing less than 5/3. Greater than 5/3, can you see that this will be positive, this will be negative, so my volume will be decreasing. That says that's my relative maximum. So the question says the dimensions of the box. Well, let's see. I guess if x is equal to 5/3, and I need to calculate, well, what is this dimension? 10 minus 10/3. So let's see, so 10 minus 10 thirds. Well, let's see, that would be 30 thirds. So that's going to be 20 thirds, would be both that dimension and that dimension. So we get a box that is 20 thirds times by 20 thirds by 5 thirds. Oops. 5 thirds. All of those are in inches. Let's see. So that's the dimensions that would create the box of greatest volume. Let me just make sure that I'm doing that calculation correctly. So x is 5 thirds inches. Then 10 minus 2 times 5 thirds, so that is indeed 10 thirds. 30 thirds minus 10 thirds, yes, is 20 thirds. Okay, last but not least, we have a container for a soft drink is in the form of a rectangular circular cylinder. If the container is to have a capacity of 12 fluid ounces, find the dimensions of the container that can be constructed with a minimum material. Okay, so if I was going to draw this container, it's going to look like that. What's the surface area of my container going to look like? Well, if you took the top and the bottom, that's pi r squared. So I have a radius here, r, and this is going to be the top and the bottom, so I have 2 pi r squared. Then what about the edge of the can? Well, if I cut down the side and then folded it out, this would be the circumference, 2 pi r, and this would be the height. So it's that plus 2 pi r h. That's the surface area. And I know that my volume of a cylinder is pi r squared h. Okay, now I know my volume is going to be 1.805 times 12, and I'd really like to minimize my surface area. So how about I solve this for h, then substitute it in here. So h is equal to this mess. That means my surface area is equal to, let's see what I have here. I have an r, and then I have a divided by r squared. I have a pi divided by a pi. So let me go ahead and erase that. If I'm multiplying all that through, I'm still going to have my 1.805 in the numerator times 2 times 12. I'll just go ahead and write that as times 24. R divided by r squared is r to the negative 1. Okay, so I'm trying to optimize this. Let me go ahead and take the derivative of it. This piece will be 4 pi r. This piece, will be negative, I suppose. Negative 1.805 times 24, r to the negative 2. Okay, so that would be undefined. This is the derivative, right? The derivative would be undefined when r is 0. Well, that kind of makes sense, because if the radius was 0, the volume wouldn't work. So I really am looking for the place this thing will equal 0. So let's see how that'll work. Why don't I divide everything in sight by 4? That means I've got pi r minus 1.804 times 6 r negative 2 equals 0. I guess I could divide everything by r as well, because r is not going to be equal to 0. If I divided everything by r, what would happen here? I'd get no r's there. Now I'd get r to the negative third there. Now I could really add this to both sides. That would be a nice sneaky trick. Wouldn't it now? Now, I'd really rather this wasn't in the denominator, so maybe I could now multiply both sides by r to the third, and I don't want this pi over here because I'm going to get r to the third over here. So I'm going to, let me put my h inside just to clarify, this is just to look at the surface area. I need to divide by pi if I'm going to keep this by itself. So what do I have here? After all that work, I have r to the third equals 1.805 times 6 divided by pi. Well, r to the third, we could see that that's going to be implying that r is the cube root, or the 1/3 power of this number here. Now, I'm not going to calculate out what this is. You could calculate it out if you wanted to use Wolfram Alpha or a calculator, but can you see that what happens here is the limits of r are 0 and something up here. This is some positive number right here. What would happen if, going back to our last simplified calculation here, what would happen if r is smaller than this number? So at that number, the surface area is not changing. So if we call this star, this is the value star. If r, this is in the denominator, right, is smaller than that number, can you see that this piece is bigger? The denominator is smaller, this piece is bigger, it's negative. If the negative piece is bigger, that means the surface area is decreasing. If the denominator is bigger, that means this number is smaller. Subtracting a smaller number means that it's increasing. That means that this is a relative minimum, and we were trying to minimize surface area. So indeed, we have our answer. Yay!